In this presentation, we'll look at how hydrogen bonding between water molecules gives water its physical characteristics. We'll look at 4 emergent properties that are the result of this hydrogen bonding and how these properties affect life on Earth. We'll also look at how water acts as a solvent and what it means for a solution to be acidic or basic. Now, in a previous presentation, we looked at how the difference in electronegativity between hydrogen and oxygen atoms results in polar covalent bonds. These are polar covalent bonds because the electrons that are shared between the atoms are shared unequally. Oxygen, which is more electronegative, attracts the electrons more strongly than the hydrogen atoms do. The result of this is that the oxygen side of the water molecule has a partial negative charge, and there are partial positive charges around the hydrogen atoms. When water molecules are in close proximity to one another, the positive part of one molecule is attracted to the negative part of another molecule. This attraction is called hydrogen bonding, and although it's a weak intermolecular force, when applied to many molecules, the force is relatively strong. This hydrogen bonding, which comes about through the polar covalent bonds, is responsible for 4 emergent properties of water that contribute to life. The hydrogen bonds that form between water molecules are transitory. In liquid water, the molecules are in constant motion, and so the hydrogen bonds only last momentarily before the molecules are again too far apart to interact. However, hydrogen bonds are forming and breaking constantly. These hydrogen bonds hold water together in a property called cohesion. The effects of cohesion can be seen if you put water on a surface that doesn't interact much with the water itself. The molecules in the middle of the droplet are hydrogen bonded with molecules all around them. However, molecules at the surface are only hydrogen bonded with other molecules that are below them. The effect of this is that all of the molecules are effectively being pulled toward each other into the center of a sphere. This often doesn't look like a sphere because it's also subject to the forces of gravity, which deforms the sphere. Gravity causes the surface of a larger body of water to be flat. A related effect is called adhesion, and this is when water molecules are attracted to molecules other than water. In a graduated cylinder, the molecules near the surface are attracted to the glass tube. In fact, they're attracted more strongly to the glass than they are to each other, and this causes the molecules at the glass interface to move upward, causing a meniscus. The pull of gravity keeps the water from climbing up the side of the graduated cylinder. However, if the cylinder is very narrow, the force of gravity is relatively weak compared to the adhesive force, and the water will move up the tube. This is called capillary action and only happens in very thin tubes. The interaction of water with whatever surface it's on is also mediated by adhesion, where the molecules in the water interact with the molecules at the surface of the solid. If the molecules on the surface are hydrophobic, they will hardly interact with the water, and the cohesive force, which attracts water to water, dominates. If the surface is more hydrophilic, and the adhesion between it and the water is greater, then the droplet will tend to spread out, as it is attracted to more of the surface. Adhesion and cohesion work together to allow trees to get water from the soil all the way up to the upper branches. As water evaporates from the leaves, other water molecules are pulled up through the trunk through cohesion. Remember that cohesion is the tendency of water molecules to be attracted to each other. So as one water molecule moves up the trunk, others will tend to follow. Adhesion also plays a very important role. The water moves up through specialized cells, actually dead cells called xylem. The xylem is narrow, and the adhesion between the water molecules and the surface of the cells allows water to travel up through capillary action. A second important emergent property of water is that it tends, in a number of ways, to moderate temperature. The first effect is that water tends to heat up and cool down very slowly. The reason for this is that heating water requires energy both to increase the kinetic energy of the water molecules and to overcome the hydrogen bonds that link water molecules together. One effect of this is that oceans or other large bodies of water tend to have very stable temperatures. The daily rise and fall of air temperatures has only a limited effect on the ocean water. The relative coolness of the ocean water in Southern California keeps the air temperatures relatively cool right at the coast. Further inland, however, we don't have such moderating effects of the ocean, and the temperatures get very hot, as we know from living inland. Water molecules are constantly moving around. However, they don't all have the same speed. Some are fast and some are slow. The average kinetic energy, however, is what we know as temperature. When water evaporates from the surface, it's the highest energy molecules that tend to evaporate, leaving behind the slower molecules. Therefore, when water evaporates, the average kinetic energy, or the temperature of the water that remains, goes down. We certainly take advantage of this effect in order to keep our bodies cool on hot days. When we sweat, water evaporates from our skin, keeping us cool. Water evaporates fastest on a dry, windy day, which is why getting out of the pool in the wind is often a very chilly affair. As liquid water cools, the kinetic energy of the molecules decrease. Like other substances, it also decreases in volume as it cools. At about 4 degrees Celsius, the hydrogen bonds between molecules begin to stabilize, but as they do, they keep other molecules at a greater distance than they would have been on average in liquid water. By the time we get to freezing point at 0 degrees Celsius, all of the water molecules are hydrogen bonded into a stable lattice. This lattice has relatively long hydrogen bonds, and as a result, the ice is less dense than water. We see this on a regular basis because we know that ice floats in a cup of water. Biologically, ice floating on water is very important as it gives organisms an ice-free habitat even during the middle of winter. As lakes and rivers freeze, they freeze from the top down, and the layer of ice on top serves as an insulator for the water below, preventing it from cooling faster. Only small, shallow ponds freeze all the way through, even during very cold winters. The ability of water to dissolve many substances is very useful for biological organisms, as most chemical reactions occur within the cytosol, or the liquid portion of the cell. Again, this is an effect of the polar covalent bonds and their effect on making some portion of the water molecule positive and some portions slightly negative. Let's start by looking at how water dissolves a crystal of salt. The salt crystal has both sodium and chloride ions, and the difference in charge holds the ions in the crystal together. As water molecules approach the edge of the salt crystal, the positive part of the water molecules interact with the negative chloride ions. As more water molecules surround the chloride ion, the negative charge in the chlorine becomes more attracted to the water and less attracted to the sodium. As it becomes less attracted to the sodium, the chloride ion is able to slowly break away from the attractive force of the sodium. Eventually, it's completely surrounded by water molecules in a sphere called a hydration shell, and that ion, we now say, is dissolved. The same thing happens to each of the sodium ions. As water surrounds them, they become attracted to the partial negative charge on the water and less attracted to the chloride ions. Eventually, they break free on their own in their own hydration shell. It's interesting to note that because of the way dissolution works, water can only dissolve other polar substances. It does not dissolve large nonpolar substances. Large molecules, such as some proteins, are able to be dissolved provided that they have a partial negative or a partial positive charge on their surface. Sometimes, in the normal course of events, a hydrogen atom that is part of a water molecule will shift from one molecule onto another water molecule. The result is a hydronium ion, which has one oxygen atom and not two, but three hydrogen atoms, and then the hydroxide ion that results from the loss of the proton. When this happens, the hydrogen atom that is transferred leaves its electron behind. Therefore, the only thing that's actually transferred is the proton of the hydrogen nucleus. The result is a positively charged hydronium ion and a negatively charged hydroxide ion. This is a reversible reaction, and so the hydronium ion can react with other hydroxide ions to reform water molecules. In pure water, the concentration of hydronium ions is only about 1 in 500 million, or 10 to the negative 7 grams per mole of water. When the concentration of hydronium ions, or hydrogen ions, increases above this level, we say that the solution is acidic. Conversely, when the concentration of hydronium or hydrogen ions decreases, we say that the solution is basic. When this happens, the concentration of OH- ions increases. We measure the concentration of hydrogen ions on a logarithmic scale called the pH scale, using this formula. By this formula, we can see that the pH of pure water is 7. We consider this to be neutral, neither acidic nor basic. Vinegar, on the other hand, is quite acidic. The concentration of hydrogen ions is high, 10 to the minus 3 grams per mole. On the other hand, bleach has very few hydrogen ions, and the pH of 13 indicates a strong base. The pH scale runs from 0 to 14, with 0 being a very strong acid and 14 being a very strong base. Most biological systems exist in the neutral area, right in the middle. Reactions that need very acidic or very basic conditions are always sequestered into separate regions so that other parts of the body or cell are not damaged by those reactions. For example, our stomach acid has a pH of about 2 and needs to be kept separate from the other liquids in our bodies. In order to maintain a pH of about 7, our bodies employ buffers. Buffers are chemicals that resist change in their pH. When hydrogen ions are added to a buffer solution, such as bicarbonate, the buffer allows the hydrogen ion to react in order to form carbonic acid. When hydrogen ions are taken out of solution, the reversible reaction moves to the right, producing more hydrogen ions. Thus, the concentration of hydrogen ions stays relatively constant even if acids or bases are added or removed from the solution.